Howdy everyone. So this video we're going to talk about automotive systems. We're going to take a systems approach to the vehicle. So when you pop open your hood, you see a lot of stuff. Now if you're familiar, it's not too foreign, but if you've never popped the hood of a vehicle before and you look at all that, that's a big mess. So I'm going to try to break things down. So even if you have seen parts and maybe you have some understanding of what's going on, hopefully I can bring light to the stuff that you don't. So let's talk about what a system is. So a system is a group of related components that are there to perform a specific function. Many things act like that, right? As far as the college goes, we are all here to perform a specific function to help you guys learn. So let's talk about things as they sort of go along. Everybody has heard about engines, so let's talk about engines first. Engine is going to be essentially our first system. Now, I'd like to use the term powertrain to really sort of be the blanket term across what we're looking at here. So right here it says 4-stroke cycle internal combustion engine, which by the way, in Canvas, you guys all have access to this presentation. So hopefully you're following along. Hopefully you've taken a look at this already. If not, you can go ahead and print it out or put it on a separate screen and follow along. We're going to talk a whole lot more about the 4-stroke cycle and what that means when we get into engines. And I'm so excited about that because that's one of my favorite subjects. But for right now, just know that our engine in an automobile, certain jet skis and motorcycles may work on what we call a 2-stroke process. We'll talk about that later. But everything that you drive that has 4 wheels is going to run on what we call the 4-stroke internal combustion process. Now, there's a whole lot of parts going on here. So if you've never seen this before, it can be overwhelming. We will get into a lot more depth, but for right now, it's going to consist of a block that is essentially our housing. Inside, we've got all kinds of stuff like crankshafts, pistons. Up on top are what we call our heads, which our head is on top of our body, so that's easy to remember. That's going to contain our valves and usually our camshaft, anything that's remotely modern or non-GM, sorry Chevy. But that is our engine, and the way things work inside is we suck in some air as well as some fuel. We squeeze that air and fuel, we ignite that air and fuel, and that explosion that happens is going to shove down these pistons, and we're essentially going to be turning some bicycle pedals, right? So our crankshaft is essentially a set of bicycle pedals. So if you've ever ridden a bike before, you know that in order to go forward, your leg needs to push down each pedal. Well, that's what your pistons are doing. They're pushing down bicycle pedals, and instead of calling it, well, your bicycle actually does call it a crank. This is our crankshaft, and it does the exact same thing. So this is our engine. Like I said, there's so much more involved, so we're going to go ahead and get into that next time. Lubrication system. Now, we do know that most of the components involved in our engine are metal. We do know that when we take components, especially metal components, and we rub them against each other, even if you take your hands at home and you rub your hands against each other, they create a little bit of heat. That's why when you're cold, you rub your hands together, right? Well, that's a problem in the engine because we're creating a whole lot more heat than you'd really like to. And that heat, also that friction, is lost energy. And if we want to be efficient, we want to take all the energy possible and put it to making power and not lose it to just heat, right? So in order to cut down on those losses, we have a lubrication system that's meant to put a barrier or a layer in between those moving components. So if I was to take 2 components and put a layer of oil in between them and then rub them together, they're going to have a lot less friction, meaning they're going to create a whole lot less heat, meaning we're going to lose a lot less energy to heat. So that's what our lubrication system is there for. It's not only there to reduce the friction, to reduce the amount of heat loss, but it's also to reduce the amount of life loss to our components. So our pistons, our cylinder walls, things like that. We want to cut down on the wear and make them last as long as possible, and that's what our lubrication system does. Not only that, but it also does help cool everything. If I'm going a little bit too quickly, just make sure you're writing down any questions. Like I said, we've got pretty much an entire lecture on each one of these systems. So this is just sort of an overall of what this class is going to be about. So please make sure you watch this video all the way through. If you are already familiar with vehicles, just bear with me. If not, take notes and make sure you're writing down any questions, and let's talk about it in the Zoom session this Thursday. So after lubrication system, we've got our cooling system. Now, I did mention that the lubrication system does help a little bit with cooling, but the main job for our cooling system is to remove heat caused by that combustion and the friction. But it also has a little sort of hidden job that not a lot of people think about, and that is to actually keep our engine at a normal operating temperature. So engines actually like to run hot. They don't like to run cold. They're not happy when they're cold. They actually are not very efficient, and they require more fuel when they're cold, and they produce more emissions when they're cold. So they're just all around not good. Not a whole lot of horsepower, not a whole lot of efficiency, and they produce too much emissions when they're cold. They like to run hot. Let me move this turbocharger out of the way here. Normal engine operating temperature is about 200 to 240 degrees Fahrenheit. That's pretty warm, right? Older engines don't run at that temperature. Newer fuel injection engines or fuel injected engines do run at that temperature, and that's totally normal. Now, anything under that 200 is actually a little bit too cold. And so when your engine first starts up, the goal is to get the engine warmed up as quickly as possible and to maintain that window. Now, when we start to exceed that 240 degrees and we start to keep going up, that's when we run into issues like overheating, and then the overheating will run into other problems like blown head gaskets, warped heads, and bad stuff like that. So we'll get into that when we get into cooling systems. Older engines are air-cooled, in some cases Volkswagen, Porsche, things like that. And oddly enough, you'd think that air cooling, man, they probably overheated a whole lot. They actually had a really hard time getting up to operating temperature, and they weren't running as warm as they should have been. And so that was actually one of the downfalls of the air-cooled engines. The liquid cooling engines actually helps regulate a whole lot better, and we'll get into that when we get into cooling systems just in general, but that's why pretty much all vehicles across the board are liquid cooled and not air cooled. It helps with regulation a whole lot more. Fuel and air systems, it's exactly what it sounds like. It's responsible, and these are all subsystems. So lubrication, cooling, fuel and air, these are subsystems for our engine. They're all there to pretty much help out or assist our engine to run the way that it should. So this subsystem is responsible for ensuring that the engine receives enough air, right? Because if you are trying to breathe, your engine, you can think of kind of like as you, it needs air. It's a big air pump. It needs to suck in air and breathe it all out. Now, besides it being an air pump, it's going to do some stuff with that air in the middle, and then it's going to need to get rid of it. So the fuel and air subsystem of our engine system, so if our engine is one big blanket system, lubrication, cooling, and fuel and air are subsystems. Our air is going to come in through our intake, and our fuel system on a carbureted vehicle is going to be regulated via carburetor. On a fuel injection or electronic fuel injection system, we are looking at a computer that's using fuel injectors, either throttle body injected or port fuel injected or direct fuel injection. We'll talk about that stuff later, so if you've never heard of that, don't worry about it. They are going to deliver fuel into the cylinder. I'm using some terms that might be foreign to you, so please write those terms down and we can talk about them during our Zoom session. So we've got air coming in, and we also have fuel coming in. So what we're going to need to do after that is squeeze that fuel and ignite it. We'll talk about how we ignite it in a little bit here in one of the electrical subsystems. Now right here, it says our engine is always trying to maintain an air-fuel mixture of 14.7 to 1, it says in your slide. If you were gonna guess 14.7 or 1, which one is your air and which one is your fuel? Think about that for a second. Which one would you guess? Well, if you guess that 14.7 is your fuel and 1 is your air, that is incorrect. That would be a whole lot of fuel to 1 air, and that's not how our engines work. In fact, they work with a whole lot of air and a little bit of fuel. So that means to every 1 part of fuel, we have 14.7 parts of air, and we're going to talk so much more about that when we get into fuel systems and electronic fuel injection. But that's essentially what our engine is always trying to do, and the reason why it tries to maintain that mixture is because that's what we call stoichiometric. It's going to be the overall best for emissions, fuel economy, and power for the gasoline that we use. That mixture will change with the type of fuel that you're using, but we'll talk a whole lot more about that in the upcoming sections. Another subsystem under engine is going to be emission controls. Now, this is probably my least favorite. I understand we need small children to breathe and trees to grow and fun things like that. So emission controls are necessary. As much as my tuners out there and my muscle car folk, you're like, boo, emission controls. We do need this to help take care of our environment. But let me tell you how it works. So first things first, your vehicle out the tailpipe, as long as it's a gasoline vehicle or, I mean, really any vehicle where it burns fuel, not electric, they're going to put out 3 big emissions. And there are other emissions, but we'll get into those probably in the second to last week. That's when we get into emission controls. CO, HC, and NOx. CO is a dangerous gas that you can actually get killed by, called carbon monoxide. Again, we'll get into this later. Carbon monoxide is going to be partially burnt fuel. HC is going to be hydrocarbons, which is essentially what you're pumping into your vehicle every time you go to get gas. And then NOx is not NOS, so please don't mix those two up because that's embarrassing. NOx is oxides of nitrogen. The X is a variable. We'll get into how those are made later on, but those are 3 emissions that are dangerous, that are emitted into our atmosphere that we need to clean up. So our emission control systems clean those up via different emission controls. The picture I have here is your catalytic converter, not Cadillac converter, catalytic converter. And that's going to help clean up these emissions, but you also have other emission controls as well, like an EGR and secondary air pump and things like that that are going to help control these same emissions. In the 70s, we realized that this was a really big problem, and so emission control devices became pretty popular on vehicles around then. And then lastly, the last subsystem in our engine main system is going to be our exhaust system. So the exhaust system is responsible for not only quieting engine operation, but also routing all those harmful gases we just talked about out the tailpipe. It's really important that our engine can breathe. If our engine can't breathe, then it can't run. So you've probably already heard about jokes of people sticking bananas or potatoes up people's tailpipes. How does that affect the engine running, you might think? Well, if you take in a deep breath, and another one, and another one, I can't breathe anymore, right? You gotta let it all out. You can't breathe in without breathing out, and that's the problem. Your engine needs the same thing. It's gotta get rid of all those gases that have already been burnt. They've already been breathed in and processed. Now we need to get rid of them, and if you can't get rid of them, your engine can't run, just like you. So it's super, super important that our exhaust is free-flowing and allows all those harmful gases out and away from the driver and out the tailpipe, hopefully already cleaned up with our emission control systems. Now, the next main system, we just got done with our engine main system. Those are all subsystems. The next main system is going to be our electrical system. The electrical system is going to consist of any component that relies on electricity for its operation. Our subsystems are going to include ignition, starting and charging, computer controls, accessory systems, also known as creature comfort sometimes, are going to fall under this same category. So let's talk about them. Our ignition system produces a high voltage spark. When I say high voltage, we could be talking around 60,000 volts. Lots of high voltage, enough to make you pee your pants. Why do we need such a high voltage? You are creating a lightning bolt, and the reason why we need that voltage, we'll talk more about what voltage is, but it really is a pressure that is pushing electrons through. We'll get into that later, but when we are trying to ignite the air-fuel mixture, we are squeezing air and fuel, and then what? We need to blow it up. Well, the only way we can blow up an ignited air-fuel mixture is by some sort of igniter. Well, in this case, it's going to be a spark plug, and in a diesel, it's a little bit different, but in this class, we're going to talk mainly about gasoline engines. And in gasoline engines, we need a spark plug to ignite that air-fuel mixture. When we ignite it, it explodes, and it does everything that we need it to. Here's the deal. It needs to be timed properly. If I ignite while I'm trying to let go of exhaust gases, that doesn't help. Or if I'm just at first taking in air and fuel, that doesn't help either. It needs to be right when it's squeezing it. And so it's really important that our ignition system is doing this in the proper timing as well. We've got a whole section and lecture on how we do this, different types of timing systems, different types of ignition systems, mechanical and electrical. So I'm really excited about getting into that. The next subsystem is going to be the starting system. And I really prefer the term cranking system because this isn't necessarily starting the engine. It's cranking the engine. So if you have ever wondered when you are turning the key and you hear that cranking sound, how is it starting the engine? How is it cranking the engine? Let me break it down. So what we have is your ignition switch, which you turn. Maybe it's a push button, maybe it's a key, whatever it might be. Right, inside of your engine, you've got a bunch of pistons moving down inside of a cylinder, right? It's moving down to suck in air and fuel. It's moving up to squeeze the air and fuel. It's blowing it up, and that's getting the piston pushed down. And then it's going to push up again to release all of those exhaust gases, and then it's going to do it over and over again. Well, here's the deal. Your engine can't start from a standstill. We need to get the action moving. We need to move the pistons at first, and then we can do everything else like squirt fuel and ignite air fuel mixtures and things like that. So in order to mechanically get the engine moving, we use the starting or cranking system. So what we're going to do is a big ring on the back of the engine that's attached to our bicycle pedals is going to be either, if it's automatic transmission vehicle, meaning you don't shift the vehicle, it's going to be a flex plate. If it's a manual transmission vehicle, it's going to be a flywheel. On the back side of your engine, you've got something like this. This encases a flex plate, and it's actually a cracked flex plate, which is probably why it's here. So on the outside, here's bolted to our bicycle pedals in the center. On the outside, we've got these little teeth. Now, these little teeth do have a purpose. These little teeth engage with an electric motor, and it turns that big wheel. So when you turn your key and you are cranking the engine, this little electric motor with a little gear pops out, and it spins that gear, and it's going to spin, in turn, our flex plate, which turns our bicycle pedals. And now that we've got the engine moving, we can start our ignition system and our fuel system, and we can get the engine running. The charging system is actually what keeps all the electronics in your vehicle running when the engine is on. This is super important. So when you first key on, right, nothing's happening, the engine has not turned on. You've got accessory, and then on, and then start, right? So accessory and on are going to power electronics through your vehicle. That is going to use your car battery, right? So if you're at the drive-in and you leave the key on for too long, I don't know how many of you have been to the drive-in lately, it's probably been a long time, but you do run into issues like potential dead batteries, right? Especially if it's a vehicle where you haven't changed the battery in a long time. When you do turn the engine on and the engine is running and spinning, the battery is kicking back and is on vacation. Doesn't do anything. While the engine is running, your charging system is running all the electronics. So your radio, your power seats, all your lights, that's your charging system. Your battery has nothing to do with that as long as the engine is running. Now, once you turn the engine off, your battery's back to work, turning all those things on. So that's why it's not a good idea to leave your battery in the on position or accessory position for too long, because you will kill the battery. So you'll notice when you go to the drive-in at the intermission, lots of people turn their vehicles on and the engine running to get their battery charged back up so they can watch their second movie, right? So that's the charging system. The other job of the charging system is to actually recharge the battery back up, but that's its last priority. So it's real important that you don't keep that key on for too long, because it does run down your battery. We will talk a whole lot more about this later. Computer control systems, in every modern vehicle, everything is controlled by computer controls. Your engine, of course, computer controls, right? But your transmission as well. Your air conditioning, guess what? Your power seats, computer controlled. Your power windows, computer controlled. It's not uncommon for newer vehicles to have in excess of 40 computers controlling things. It's crazy, right? But it is also one of the most efficient ways to control things. Computers can make decisions a whole lot faster than anything mechanical, and they do tend to last quite a bit longer than a lot of mechanical things. Computers don't generally go out unless something else caused them to go out. So it is an efficient way to run things. Some people worry about them because they're a bit more complicated, but that's what we have the computer controls class for. So our computer control system is going to provide the best drivability, meaning when you go to start your vehicle, did it start right up? Did you have to pump the gas pedal 3 times, tap on the dash, and say some sort of chant to get your car to start? No. Cold morning, middle of winter, you go to start that car, boom, starts right back up. That's because of beautiful computer controls and fuel injection. So drivability is how easy is it for the driver to drive the car. The next thing is emissions. Computer controls can control things so finite that mechanical things can't, and so we're able to have much cleaner emissions coming out of the tailpipe, as well as fuel economy. So fuel economy and emissions sort of go hand in hand. If we are getting good fuel economy, we're generally going to get good fuel emissions, or just exhaust emissions in general. And computer controls help us do that. We do have a whole section on how computer controls work, and so we will get into that later in the semester. And as I mentioned, we have many, many computers controlling everything. So the way computers are going to work is we've got inputs with sensors telling the computer, all right, this is what's going on. The computer is the big boss that says, all right, if I've got these conditions going on, it's 70 degrees outside and I've got this much air coming in, this is how much fuel I'm going to send out. And that's how computer controls generally work. But like I said, we have a whole hour or so long lecture on how computer controls work this semester.